Good evening everyone, good evening. I welcome you all again to NEET Elite. I hope you guys are doing great, having a good time. So people, you can first of all let me know in the chats if I'm audible and visible to everyone, right? Hello Ishpreet, hi Anil, hello Ashwarya, hi Chitra, hello Tanzila, hello Dark Angel, hi Aisha, hello Yuvashri, hi Chandan, hello Fazan, hello Ajay. Welcome back my dear elites, welcome back. Just let me know in the chat box first of all if I'm audible and visible to everyone, yeah? Hello Akash, hello Ubad, hello Jesus child. Welcome back everyone, welcome back. Just give me some green signal from the chat so that I'll get to know that I'm audible and visible to you properly. Yes people? Perfect guys, perfect. So as you all must be knowing, tonight it's going to be our second session from the chapter General Organic Chemistry, right? In the last session, we exactly saw the stability of the charged species, right? Yes, we exactly got to know the stability of charges on different species, and there were two important points if you remember. Whenever you need to compare the stability of the charges on the elements which belong to the same period, we decide that on the basis of electronegativity, right? Negative charge on more electronegative element is considered to be more stable, right? And positive charge on less electronegative element is considered to be stable when we need to compare the stability of the charges on the elements which belong to the same period, right? Similarly, when we need to compare the stability of the charges on the elements which belong to the same group, we decide on the basis of volume charge density, right? Wherever volume charge density is going to be minimum, there only stability of the charge is going to be maximum, right? That's something which we discussed in the last session if you remember, correct? Right people? Exactly. So in the tonight's session, what we are going to cover something called as inductive effect, which is one of the most important effects as far as your general organic chemistry is concerned, right? But before going into the inductive effect, we'll try to solve certain questions, and after that we'll move on to our actual topic of the tonight's session, which is what we call as inductive effect, okay? Alright, before starting the session, the ones who have just joined in, who are new to the channel, let me introduce myself. Well people, my name is Wassim and I'm your chemistry master teacher right here on this NEET Elite channel, yeah? The ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this NEET Elite channel, yeah? So do like the video, share the video with friends, and do subscribe to the channel as well, okay? Perfect. So people, you can let me know in the chats if you guys are super duper excited about the tonight's session as well, right? Hello Noreen, hello Soumya, hi Dakshin, hello Kailash, hi Rishita. Welcome back. Ajay, I do not remember the page on NCERT on which this topic is given. Well, I'll check it out tonight. I'll let you know in the next session, like on which page in the NCERT it's given to us, yeah? Perfect guys, so let's get going. Let's get started with the tonight's session, in which I'll first of all show you how to compare the acidic strength of different species, okay? So first of all, we'll get to know the concepts which we discussed in the last session, right? It is going to be one of the application of that concept which we discussed in the last session, right? Comparison of acidic strengths, okay? On the basis of the stability of the charges present on the ions. Let's have a look. Let's have a look guys. See exactly what I'm going to talk about, and do take a note of everything which I'll be mentioning on the screen, okay? See guys, for example, I'm taking a general acid as HA. Let's say I'm taking a general acid as HA aqueous, okay? Right? See, there are many definitions given to the acid. One of the definition for the acid is any substance which can donate H positive, any substance which on dissolving in water donates H positive is something which we call as acid, right? That is one of the definitions of the acid, right? Any substance which has got the tendency to donate H positive can behave like the acid, okay? See guys, for example, this acid which I've taken over here, this is the acid, general acid which I've taken over here. Let's say I'm dissolving it into water. What it's producing H positive ion, and with this you are getting a negative ion over here, right? This acid, after donating H positive ion, right, it's going to be left with a negative, right? Okay, so this acid over here, it has donated H positive, right? After donating H positive, this acid got converted into a negative. So after donating H positive, the acid is getting converted into a negative, right? See, this is the acid which we have taken. And after the donation of H positive, this acid is getting converted into A negative. This A negative is what we'll be calling as conjugate base of the acid which we have taken over here, right? This is something which we'll be calling as conjugate base of the acid which we have taken into consideration over here, right? See, this HA, it is the general acid. After the donation of H positive, this acid got converted into A negative. This A negative is something which we call as conjugate base of this acid. As simple as that, right? Similarly, for example, I have got a general base as BOH. Let's say it is a general base, right? Okay, any substance which can donate OH negative ion can be called as the base, right? This is the general base which we have taken. So after the donation of OH negative, this BOH is going to get converted into B positive, right? So this B positive, see, if this was a base, after the donation of OH negative, this base got converted into B positive. This B positive is something which I'll be calling as conjugate acid of this base over here, right? As simple as that. Now we will understand what all things I'm going to talk about. I'm not going to talk about this base, I'm going to talk about the acid, right? Well, there are certain questions which can be asked about the strength of the acid, right? Do remember one thing, strength of acid is directly proportional to the stability of the conjugate base formed. Stability of the acid is directly proportional to the stability of the conjugate base which got formed, okay? More stable the conjugate base, stronger is going to be the acid, right? Do remember this thing over here, right? Acidic strength of the acid, it depends on the stability of the conjugate base, right? More the stability of the conjugate base, more is going to be the strength of the acid which we have taken into consideration. Point number one. On this point, I'm going to solve many of the concepts. Right? Again, I'm telling you, strength of the acid is directly proportional to the stability of the conjugate base. More stable the conjugate base, more is going to be the strength of the acid, right? Let's have a look how this concept is to be used and questions are to be solved from this concept, right? Have a look, guys. Have a look properly what I'm going to talk about. I have taken many questions over here, right? Let's try to solve these questions on the basis of this simple concept which I have given you, right? See, I'm given with something called as ROH, then we have got RSH, okay? So I'm going to decide which among the two is going to be the stronger acid. I'm going to see which among the two is going to be stronger acid, right? So first of all, how do I check the strength of the acid? Strength of the acid is decided on the basis of the stability of the conjugate base, right? So first of all, I'm going to make the conjugate base of this acid, then I'll be making conjugate base of this acid. Once I make the conjugate base of both these acids, I'll then compare the stability of the conjugate bases. Wherever stability of the conjugate base will be more, there only acid is going to be stronger. As simple as that, right? So first of all, if I try to make the conjugate base of this acid, this ROH over here, what is going to be its conjugate base? After the removal of H positive, this ROH, it gets converted into RO with a negative charge on oxygen, right? Similarly, after the removal of H positive over here, it gets converted into RS with a negative charge on sulfur. As simple as that, right? Well, this is the conjugate base of this acid and this is the conjugate base of this acid. Let's try to compare the stability of these conjugate bases. Have a look, guys. Understand properly. See, over here we have got the negative charge on oxygen and over here we have got the negative charge on sulfur. Oxygen and sulfur, they belong to same group as you all must be knowing. Oxygen and sulfur, they belong to same group as you all must be knowing, right? Whenever we need to compare the stability of the charges on the elements which belong to same group, we take volume charge density into consideration. And volume charge density, as you all must be knowing, it is directly proportional to the charge present on the species and inversely proportional to the size of the species, right? Now, among oxygen and sulfur, where will be the size more? Can I say sulfur will be having more size than that of oxygen? If sulfur has got more size, that means sulfur over here, this Rs negative, it will be having less volume charge density. And volume charge density is inversely proportional to stability. I hope you remember, right? So if sulfur, if this Rs negative has got less volume charge density, I'll say its stability will be more. So stability of this conjugate base is more than that of the first one, right? Wherever stability of the conjugate base is more, its corresponding acid is going to be more stronger, right? So I'll say this is going to be the acidic strength order, correct? As simple as that, right, people? You can let me know in the chats if it's clear to everyone so that I can move on to the next question. Yeah, let me know fast in the chats. Let me know fast in the chats if it's clear to everyone. I have drawn simply the conjugate bases of these acids, and I compare the stability of the conjugate bases, right? This conjugate base was found out to be stable, right? So its acid is going to be stronger compared to this ROH. As simple as that, right? Okay. Now we will have a look. Let's try to compare the stability of, let's try to compare the acidic strength in the second case, okay? So how do we compare the acidic strength? By seeing the stability of the conjugate base, right? So what I'll be doing? I'll be removing H positive from here. If I remove H positive from here, this CH4, it gets converted into CH3 with a negative charge on this carbon. Similarly, after removing H positive from here, this NH3 is going to get converted into NH2 with a negative charge on nitrogen. Similarly, take H positive out from here, it's going to get converted into OH with a negative charge on oxygen. Similarly, take H positive out from here, you will get fluorine with a negative charge, right? So first of all, you have formed the conjugate bases of these acids which are given to us, right? Okay, we have made the conjugate bases. Now let's compare the stability of these conjugate bases. Have a look. Over here we have got the negative charge on carbon, right here negative charge on nitrogen, right here negative charge on oxygen, and right here negative charge on fluorine, right? So carbon, nitrogen, oxygen and fluorine, they are the same period elements, right? They are the same period elements. Whenever we need to compare the stability of the charges on the elements which belong to the same period, we decide it on the basis of electronegativity. We know negative charge is more stable on more electronegative element, right? And fluorine being the maximum electronegative element among all, followed by oxygen, followed by nitrogen, followed by carbon, right? So can I say negative charge will be more stable on more electronegative element, and this is going to be the stability order of these conjugate bases. And whatever is going to be the stability order of the conjugate bases, same is going to be the acidic strength order in this case, right? I'm sure it is clear to everyone. Yes? Right, people? Now, let's have a look on the third case. Let's try to make their conjugate bases. Water. After removal of H positive, this water gets converted into OH negative. This is the conjugate base of this water. H2S. After removal of H positive, it gets converted into SH with a negative charge on sulfur, right? Okay, so these are the conjugate bases of these acids which we have taken over here, correct? Let's compare the stability order. Negative charge on oxygen, negative charge on sulfur, right? Oxygen and sulfur, they belong to same group, right? So volume charge density comes into play, right? See, sulfur has got more size, so its volume charge density will be less the volume charge density, more the stability. So this is basically the stability order of these conjugate bases, and whatever is going to be the stability order of the conjugate bases, same is going to be the acidic strength order. I'm sure it's clear to everyone, right? Okay. Similarly, let's talk about the fourth case. Let's see the acidic strength order in this case. Have a look. Let's take H positive out from here. After taking H positive out, there'll be negative charge on this carbon, right? After taking H positive out from here, there'll be negative charge on this carbon. After taking H positive out from here, there'll be negative charge on this carbon, right? Okay. In the last session, we saw the electronegativity of a triple bonded carbon is more than that of a double bonded carbon, which is more than that of single bonded carbon, right? Yes? Electronegativity of a triple bonded carbon will be more than that of electronegativity of a double bonded carbon, which will be more than that of electronegativity of a single bonded carbon, right? And negative charge is more stable on more electronegative element, right? So this carbon being more electronegative among all, right? Negative charge on this carbon will be more stable. So conjugate base of this acid will be more stable. Whatever is going to be the order of the stability of the conjugate bases, same is going to be the order of what? Same is going to be the order of their acidic strengths. As simple as that, right? Okay. Now we will have a look in this case. See, if I take H positive out from here, it will get converted into R. This is C, this is triple bond C, and there's a negative charge on this carbon, right? Similarly, if I take H positive out from here, it gets converted into N. This is H2 and nitrogen having the negative charge, right? First of all, if I ask you, what about the electronegativity of this carbon? What about the hybridization of this carbon? You'll say sp. It's sp hybridized. If I ask you, what about the hybridization of this nitrogen? It is forming 3 sigma bonds, 1 lone pair. So steric number is 4. If steric number is 4, it is sp3 hybridized, right? This is sp3 hybridized nitrogen. Let me first of all tell you one important point. See, remember the electronegativity of sp hybridized carbon is always more than that of electronegativity of sp3 hybridized nitrogen. Do remember this fact, okay? This is experimental, right? Electronegativity of sp hybridized carbon is always greater than that of electronegativity of sp3 hybridized nitrogen, right, people? Now have a look exactly. See, I've taken H positive out from here, so this is the conjugate base. I've taken H positive out from here, so this is the conjugate base, right? See, carbon and nitrogen, they belong to same period, right? They belong to same period. And whenever we need to compare the stability of the charges on the elements which belong to the same period, right? Electronegativity comes into play. Yes. Now we will have a look. Have a look. Negative charge is more stable on more electronegative element. If I'll ask you which element among the two atoms are more electronegative, I'll say this sp hybridized carbon, its electronegativity is more and negative charge is more stable on more electronegative element. So this is the stability order of the conjugate bases, and whatever is going to be the stability order of the conjugate bases, that is going to be the order for the acidic strength over here, right? I'm sure it's clear to everyone. You can let me know in the chats if it's clear to everyone so that I can move on fast. I'm sure exactly how you got to know, like how do we compare the acidic strengths of different acids, right? Based on the stability of the conjugate bases. As simple as that, right? Yes? Someone is saying Mera jacket. Is it your jacket? Perfect, guys. Should I move on? Let me know fast in the chats. Yes. Perfecto. Let's move on to the concept which we have to discuss in the tonight's session, right? Okay. So people, tonight actually we are going to discuss one important concept. That's something which we call as inductive effect, okay? Right? One of the most important topics of this chapter. And it's simple at the same time, right? Have a look properly, and whatever, again I'm telling you, whatever I'll be mentioning on the screen, I want you guys to take a note of every single thing which I'll be noting down on the screen, right? Yes? Alright, I'll show you the homework which I gave in the previous session. No issues at all, right? Okay, have a look, guys. Let's talk about something called as inductive effect, and let's have a look on certain parameters which I have mentioned on the screen. Have a look first of all. See guys, let's try to have a look on the definition. See guys, as per the definition of inductive effect is concerned, whenever any atom or group is bonded to a carbon chain, the entire chain becomes partially polarized, right? The entire chain becomes partially polarized because of sigma electron transmission, and this effect is something which we call as inductive effect. What is meant by this? You'll get to know in some time. Just give me some second. One more point, it is measured always with respect to hydrogen atom, right? Let's try to decode these two statements which I'll mention on the screen, right? Let's try to understand them properly, okay? See guys, over here I have taken a carbon chain. This is a carbon chain of 4 carbon atoms, right? And with this terminal carbon, hydrogen is attached. Right? And in this carbon, everywhere you are seeing the sigma bonds. This is carbon sigma bond, this is sigma bond, this is sigma bond, right? That means in this carbon chain, there is only sigma electron density, right? There is only sigma electron density in the carbon chain. Yes, there is only sigma electron density in the carbon chain, right? Okay. Now what I've done over here, I've replaced this hydrogen atom, by some atom or group of atom Y. I'm going to replace this hydrogen atom by some atom or group of atoms Y. And over here, this Y is again attached with the same carbon chain, right? And over here, again, you have got only sigma bonds present. So there is only sigma electron density present in the carbon chain, right, people? Okay. Similarly, I'm again going to remove this hydrogen. I'm again going to replace this hydrogen by an atom or a group of atoms X, right? Again, if you see the carbon chain, there are only sigma bonds present in it, right? There is only sigma bonds present in it. So basically in this carbon chain, again, you have got only sigma electron density. Yes? Now have a look what I'm going to talk about. Let's assume the sigma electron density in this carbon chain is equal to A. A is the sigma electron density in this carbon chain. Let's assume B is the sigma electron density in this carbon chain. Let's assume C is the sigma electron density in this carbon chain, right? A is the sigma electron density in the carbon chain when the terminal atom is attached to hydrogen. B is the sigma electron density in the carbon chain when the terminal carbon is attached with some atom or group of atoms Y, right? Similarly, C is the sigma electron density when this terminal carbon is attached with some atom or group of atoms X, right? That's something which I've done till here, right? Now guys, understand. If I say B is less than A, if I say B is less than A, what does that mean? That means the sigma electron density in this carbon chain is less than that of sigma electron density in this carbon chain, right? Right? A is the sigma electron density in the carbon chain when the terminal atom is attached with hydrogen. B is the sigma electron density in this carbon chain when this hydrogen is replaced by some atom or group of atoms Y, right? I'm assuming B is less than A, right? That means sigma electron density in this chain is less than that of sigma electron density in this chain, right? So what can I conclude from that? What can I conclude from that? If the sigma electron density in this chain is less than that of this one, what can I conclude? That means on the replacement of hydrogen with this Y, sigma electron density in this chain has got decreased, which is only possible if this Y can pull the sigma electrons towards itself, right? Yes? So I can clearly say something like this. I'm assuming sigma electron density in this chain is less than that of sigma electron density in this chain, right? That's only possible if Y could have pulled some of the sigma electron density towards itself, right? Okay, so basically Y has pulled some sigma electron density towards itself, right? If Y is pulling some sigma electron density towards itself, I'll say Y will get delta negative charge because electron density towards Y, sigma electron density towards Y would have got increased, and that increase in the sigma electron density towards Y is represented by delta negative, right? So which charge will come on this carbon? There will be delta positive charge coming on this carbon. Similarly, there will be delta positive on this carbon. Similarly, there is delta positive on this carbon, right? As simple as that. Right, people? Yes? Right? So basically what has happened? What has happened? Understand, read the definition again. Whenever any atom or a group is bonded to a carbon chain, the entire chain becomes partially polarized, right? By introducing the atom or group Y, has the chain become partially polarized, right? Every carbon has got partial positive charge over here. I'll say this chain has got partial positive charge by the introduction of some atom or group Y over here, right? Okay, so remember, whenever any atom or group of atom is introduced in the carbon chain, which makes the carbon chain partially polarized, right? This inducement of the charges in the chain, this inducement of the partial charges in the chain, right? This is something which we actually call as inductive effect, right? Okay. And people, at the same time, has this group increased the sigma electron density in the chain? No, it has decreased the sigma electron density in the chain. Do remember, that group which decreases the sigma electron density in the chain, we say that group exhibits minus inductive effect. That group shows minus I effect, right? As simple as that. Okay. Now similarly guys, one more thing. See, sigma electron density in this carbon chain is equal to A. Sigma electron density in this carbon chain is equal to C, right? And what I have done, I have replaced hydrogen with this atom X or group of atoms X, right? Now let's assume C is greater than A. Let's assume C is greater than A. right? Let's assume sigma electron density in this chain is more than that of sigma electron density in this chain, right? When is that possible? When is that possible? I'm telling you a simple thing. When I've replaced hydrogen by some atom X, right? Then I'm seeing, for example, electron density, sigma electron density in this carbon chain is greater than that of sigma electron density in this carbon chain. That is only possible if this X would have pushed some electron density, some sigma electron density in the chain, right? So what is this X doing over here? It's pushing the sigma electron density towards the chain. If X is pushing the sigma electron density towards the chain, right? I'll say sigma electron density in the chain would have got increased, and that increase in the electron density is represented by delta negative charges, right? Okay, so this X, it has introduced some more sigma electron density in the chain, right? And whenever you'll be having such kind of a group which increases the sigma electron density in the carbon chain, right? That group or atom we say is exhibiting plus inductive effect, right? Okay, I'm sure you got to know what this inductive effect is all about, and what this plus I is all about, and what this minus I is all about. Minus I showing group is going to decrease the electron density, is going to decrease the sigma electron density in the chain, and plus I showing group is going to increase the sigma electron density in the chain, right people? You can let me know in the chats if it's clear till here, so that I can move on and talk about this a bit more in detail, right? Let me know first in the chats. Yes, perfect. Perfect, guys. Okay. Sir, you said inductive effect is valid for only 3 carbon atoms. I did not say that yet. I did not say that yet. That's something which I'm going to tell you in some time, right? Just wait for that. Okay. Now people, let's move on. Let's talk about a few more interesting things, yeah? Right? That group of atom which decreases the sigma electron density in the carbon chain shows minus I effect, and that group or atom which increases the sigma electron density in the chain shows plus I effect, right? Yes, that's something which we have discussed. Now people, have a look. Plus I and minus I effects, they are relative to each other. What is meant by this term? This is again important. Plus I and minus I, these are relative towards each other. What it exactly means. See guys, let me make you understand this statement in the form of 2 examples, right? Okay, so before talking about this example, let's have a look on this example. Let's have a look on this example, right? See, if I talk about this carbon atom and this carbon atom, right? This carbon, it's forming 2 sigma bonds basically. So the hybridization of this carbon is going to be sp. If I'll ask you what is the hybridization of this carbon, you'll clearly say it's sp2 because it's forming 3 sigma bonds, one here, and one with hydrogen, right? So it's forming 3 sigma bonds, sp2 hybridized, right? If this carbon is sp hybridized, its percentage S character is 50. If this carbon is sp2 hybridized, its percentage S character is 33%, right? And more the S character, more the electronegativity, right? We have discussed that in the earlier sessions. So people, if this carbon has got more S character, I'll say the electronegativity of this carbon is more. If electronegativity of this carbon is more, this carbon is going to attract the bonded pair of electron towards itself, or I'll say the sigma electron density will shift towards this carbon. When the sigma electron density shifts towards this carbon is going to get delta negative, and at the same time this carbon is going to get delta positive, right? So people understand, if I talk about this group in particular, is this group increasing the sigma electron density over here or decreasing? It is decreasing the sigma electron density, right? This group is decreasing the sigma electron density. It is pulling the sigma electron density towards itself. So this group over here, can I say it is simply showing minus I power? It's showing minus I effect, right? What is this group doing? What is this group doing? Can I say this group is pushing the sigma electron density towards this one, right? So this group is exhibiting plus I effect, right? I can say something like this. I can say this group is showing minus I with respect to this group, and this group is showing plus I with respect to this group. Can I say both this plus I and minus I, these are relative to each other, right? As simple as that. See, this group is showing minus I with respect to this group, and this group is showing plus I with respect to this group. So I can clearly say both plus I and minus I, these are related to each other. That's all, right? Yes? Similarly, guys, if you talk about this carbon atom and this carbon atom, is the electronegativity of both these carbon atoms going to be same? we have discussed in the last session. Can you let me know? Is the electronegativity of both these carbon atoms going to be same? Just let me know fast in the chats. Is the electronegativity of both these carbon atoms going to be same or different? It's absolutely going to be different, right? See, I'll say this ring over here, right? It is under more strain. So electronegativity of this carbon atom will be definitely more. Electronegativity of this carbon will be comparatively lesser than that of this one, right? Because this group, this ring over here, it's under more strain, right? It's under more angle strain. Yes? Right? Now have a look exactly. If this carbon is more electronegative, it's going to pull the sigma electrons towards itself, due to which this ring over here, this group over here, it's showing minus I effect with respect to this one, right? And what this group is doing, it's pushing the sigma electron density towards this group. That means this group is showing plus I effect, right? So simple. This group is showing minus I with respect to this group, and this group is showing plus I with respect to this group. So both minus I and plus I, these are again, we can say, relative towards each other. That's all. As simple as that, right, people? Okay, I'm sure this statement is also clear to you, right? Do remember one more thing. All the cationic groups, what do we mean by the cationic groups? Any group having positive charge on it. Say, this is Nr3 having positive charge on it, OR2 having positive charge on it, this NF3 having positive charge on it. Any group having positive charge on it are going to show always the minus I effect, right? That means whenever these groups are attached to the carbon chain, they are going to pull the sigma electron density towards itself, right, from the carbon chain. And any group which pulls the sigma electron density from the carbon chain towards itself, that group always shows minus I effect, right? So any group carrying the positive charge, that means if I talk about the cationic group always shows the minus I effect, right? I'm talking about some common minus I showing groups, and these are some common minus I showing groups, point number 1, right? Point number 2, do remember one more thing, minus I power of the cationic group is always greater than the minus I power of the neutral group, right? Yes, right? Minus I power of the cationic group always is going to be greater than minus I power of the neutral group, right? That means whenever cationic group is attached to a carbon chain, this cationic group will be having more tendency to drag the sigma electron density towards itself as compared to the neutral group if attached to the same carbon chain. Right, people? Okay, as simple as that. Okay, so do take a note of this statement as well. It's important. Minus I power of the cationic group is always greater than minus I power of the neutral group, right? Okay, all the halogens, be it fluorine, be it chlorine, be it bromine, iodine, right? All the halogens, they are going to show minus I effect. That means whenever any halogen is attached to a carbon chain, halogen is going to drag the sigma electron density from the carbon chain towards itself, due to which partial polarization will happen in the carbon chain, right? And I can clearly say the halogen has decreased the sigma electron density in the carbon chain, which makes the halogen showing minus I effect, right, people? Yes, again the same thing. Now one more thing. Groups like OH, NH2, NO2, CN, C double bond O, C double bond OH, C double bond OR, C double bond OR, right? All these groups are going to show minus I effect. Why they show the minus I effect? Have a look, people, properly. See, for example, I have got a group, OH group, attached with a carbon chain. Let's say this is the carbon chain. And towards this carbon chain, for example, I'm attaching this OH group. Right? I've attached OH group in the carbon chain, right? Now have a look properly. See, if you talk about this terminal carbon, this terminal carbon is attached with oxygen. Can I say oxygen is more electronegative than carbon? If oxygen is more electronegative than carbon, can I say oxygen will attract the bonded pair of electron towards itself, right? If oxygen attracts the bonded pair of electron towards itself, can I say there'll be displacement of sigma electrons towards the oxygen, right? Can I say this OH is basically decreasing the sigma electron density in the chain, and any group which decreases the sigma electron density in the carbon chain, we say that group shows minus I effect. So this OH simply shows minus I effect, right? Again, if this NH2 is attached with the same carbon chain, again nitrogen will be more electronegative than that of this carbon. So nitrogen is going to again attract the bonded pair of electron towards itself. It's going to pull the sigma electrons towards itself, right? And when nitrogen pulls the sigma electron towards itself, I'll say this NH2 group, it decreases the sigma electron density in the carbon chain. So again, I'll say this group shows minus I effect, right? As simple as that. Similarly, if you talk about NO2, again minus I. If you talk about this CN, what is going to happen, right? If I attach CN towards this carbon chain, what is going to happen? Understand. See guys, this CN means it is going to be C triple bond N, right? We have seen the bond order of CN. CN, right? CN contains 14 electrons, and any 14 electron species is always going to have the bond order 3, which we have discussed in the chemical bonding few days back only, right? See, basically this carbon, it has got 2 more hydrogens attached with this. This carbon has got 2 more hydrogens. This carbon has 2 more. This carbon has 3 more hydrogens attached with it, for example, right? Now people have a look. See what I'm going to talk about. Okay, see, if you talk about this carbon in particular, can I say this carbon is forming 1 and 1, 2 sigma bonds, right? 2 sigma bonds, that means the hybridization of this carbon is sp. If you talk about this carbon in particular, it's forming 1, 2, 3 and 4 sigma bonds. So this carbon is going to be sp3 hybridized, right? If this carbon is sp hybridized, its percentage S character is more. If percentage S character is more, that means electronegativity of this carbon is more. If electronegativity of this carbon is more, that means this group in particular, it's going to pull the sigma electron density towards itself, which makes this group again showing minus I, right? Okay, so this group, the CN, it's again going to decrease the sigma electron density in the chain. So this group clearly shows minus I effect, right? Okay, similarly, if you will be having C double bond O attached with the carbon chain, let's assume this is the carbon chain over here, right? And with this carbon chain, you have got this C double bond O attached, right? See guys, can I say something like this? C double bond O, correct? Can I say oxygen is more electronegative than carbon? If oxygen is more electronegative than carbon, that means oxygen will drag the oxygen will drag the bonded pair of electrons towards itself, due to which oxygen gets delta negative charge, carbon gets delta positive charge. If carbon is getting delta positive charge, so this carbon now will be having more tendency to drag the sigma electrons towards itself, right? Because this carbon now has got delta positive charge. So this carbon will be having now more tendency to drag the sigma electrons out of the carbon chain, which makes this group again to show minus I power, right? Okay, so this group is again decreasing the sigma electrons in the carbon chain, right? So this group again shows minus I. Similarly, when this group is attached to the carbon chain, it is going to show minus I. When this group, minus I, right? When this group, again minus I. Because everywhere, there will be delta positive here, there will be delta negative here, delta positive here on this carbon, delta negative here, similarly delta positive here, delta negative here, right? I'm sure it's clear to every single guy. Yes? Right, people? I'm sure it's clear to everyone, right? Perfect. All right, my dear elites. Let's move on. Let's talk about a few more important things. Now we are going to talk about those groups which always show plus I effect, right? Remember, whenever you'll be having a group which will be having a negative charge on it, that means I'm talking about the anionic group. Whenever I'll be talking about the anionic group, whenever I'll be talking about that group which carries negative charge on it, that group is always going to show plus I power. That group is always going to increase the sigma electron density in the carbon chain towards which the group will be attached, right? Yes? Okay, so all the anionic groups like your CH2 negative, like NH negative, like O negative, these are going to simply show the plus I effect. They are going to increase the sigma electron density in the carbon chain when they'll be attached towards any of the carbon chain, right? As simple as that. Now, the way we talked in the minus I power, I told you the minus I power of the cationic group is always greater than the minus I power of the neutral group. In the similar way, I'm telling you, the plus I power of the anionic group is always greater than the plus I power of the neutral group, right? Okay, see, whenever an anionic group is attached to the carbon chain, right, it is definitely going to increase the sigma electron density in the carbon chain, right? Okay, and the anionic group, it has got more tendency, it will increase the sigma electron density more in the carbon chain as compared to when the carbon chain was attached with the neutral group showing plus I, right? So if I'll be having the neutral group attached with the carbon chain and at the same time an ionic group attached with the carbon chain, which group is going to increase the sigma electrons more in the carbon chain? The anionic group is going to increase the sigma electron density more in the carbon chain, right? As simple as that. Perfect. Similarly, all the alkyl groups, they show plus I effect. All the alkyl groups show plus I effect. Let's talk about this one as well. Okay, I'm sure till here everything is clear. People, is everything clear till here? Should I move on to this? All the alkyl groups, they are going to show plus I effect. That means all the alkyl groups, they are going to increase the sigma electron density in the carbon chain, right? Let's have a look how. See guys, let's have a look how. See, this is the alkyl group, this is the methyl group, right? This is the methyl group. See, if I talk about CH4, if I take one of the hydrogen out from here, right? If I take one of the hydrogen out from here, it becomes CH3, that's called as methyl, right? In short, whenever you'll be having the alkane, if you take one of the hydrogen out of it, it becomes alkyl. It becomes alkyl. When you take one of the hydrogen out from an alkane, it becomes alkyl, right? Yes? Now have a look. This CH3, it's an alkyl group. It's a methyl group basically, right? It's a methyl group, which is attached with the carbon chain, right? I'm telling you all the alkyl groups, be it methyl group, ethyl group, propyl group, whatever alkyl group I'll be having, it's always going to show plus I effect. Why is that? Have a look properly. See, this is the carbon chain over here, right? This is the carbon chain over here. Let's say this is the terminal carbon of the carbon chain, right? Which is attached with this carbon chain. There'll be a bond pair exactly at the center, which you all must be thinking, right? You all must be thinking the bond pair is going to be exactly present at the center because there is a covalent bond between these two carbons. That's what you'll be thinking, correct? But at the same time, people, if I'll ask you among carbon and hydrogen, which one is more electronegative? You'll say carbon is more electronegative, right? Yes? Right, people? You'll say carbon is more electronegative. If carbon is more electronegative, that means this carbon has got more tendency to attract this bonded pair of electron towards itself, right? Due to which this carbon is going to get delta negative charge. Again, due to this bond, the carbon is going to get delta negative charge. Again, due to this bond, the carbon is going to get delta negative charge. So basically, what about the charge present on this carbon atom? It is going to be delta negative in short, right? There'll be negative charge on this carbon. Can I say this negative charge is going to repel this bonded pair of electrons, right? If this negative charge repels this bonded pair of electron, right? Which is basically the sigma electron pair, So there's a repulsion between this negative charge and this electron pair over here. Can I say this electron pair due to repulsion will be pushed towards the carbon chain, right? So what is happening? What this alkyl group is doing? It is increasing the sigma electron density in the carbon chain. And whenever we'll be having any group attached with the carbon chain, increasing the sigma electron density in the carbon chain, we say this group shows plus I effect, right? So all the alkyl groups which we'll be having, they'll be always going to show plus I effect. I'm sure it is clear to everyone, right, people? You can let me know in the chats fast. Yes? Right, let me know fast in the chats. Okay, now we will have a look. Let's move on to a few more important things. Now there is one more point. Plus I power of any group is directly proportional to the number of branching at the free valent carbon atom, right? What does this statement mean? First of all, let's talk about what this free valent carbon is all about, right? Let's have a look about the free valent carbon. What is this free valent carbon all about? See guys, see. If I talk about this carbon in particular, I'm assuming this carbon is attached with the carbon chain. This is the carbon chain over here, right? This is the carbon chain over here, correct? Right? This carbon is attached with the carbon chain, so I'll be calling this carbon as the free valent carbon, right? Similarly, for example, this carbon is attached with the carbon chain over here, so I'll be calling this carbon as the free valent carbon, right? As simple as that. Okay. Now people, plus I power, it's directly proportional to the branching at the free valent carbon atom, right? See, at this free valent carbon, how many branches do we have? This is one of the branch, this is one of the branch at this free valent carbon, right? At this free valent carbon, how many branches do we have? This is one branch, this is one branch, this is one branch, right? So what is going to happen basically? What is going to happen? Basically, I told you a few minutes back, all the alkyl groups, they increase the electron density, right? So basically, this CH3 is going to push the sigma electrons towards this carbon. This CH3 is going to push the sigma electrons towards this carbon. This CH3 is going to push the sigma electrons towards this carbon, due to which there will be negative charge on this carbon, right? Similarly, this alkyl group, it's again going to push the sigma electron density towards this carbon, and this CH3 is again going to push the sigma electron density towards this carbon, due to which this carbon gets delta negative, right? If I ask you, where will be the magnitude of negative charge more, on this carbon or on this carbon? I'll say the magnitude of negative charge will be more on this carbon, right? Why is that? Why is that? Because over here you have got more alkyl groups attached which increase the electron density towards the carbon, right? So I can say if negative charge is more on this carbon, that means there will be more repulsions between negative charge and this sigma electron pair. If there are more repulsions between negative charge and this sigma electron pair, in this case, I can say the sigma electron density in this carbon would have got increased, right? Similarly, in this carbon chain also sigma electron density would have got increased, but in this case, the repulsions between negative charge and this sigma electron pair, its magnitude is more, right? So sigma electron density in this carbon chain will be more, right? As compared to the sigma electron density in this carbon chain, right? So can I say something like this? Can I say this group in particular has got more tendency to increase the sigma electron density in the carbon chain, right? And that group which has got more tendency to increase the sigma electron density in the carbon chain, that group has got more plus I power. So plus I power of this group will be definitely greater than that of plus I power of this group, right? So do remember one thing, plus I power of the group is directly proportional to the number of branching at the free valent carbon atom, right? Okay, more the branches present at the free valent carbon atoms, right? More is going to be the overall plus I power of that group, as simple as that. Let me know fast in the chats if it's clear to everyone so that I can move on and talk about a few more interesting things. Yes? Let me know fast. Let me know fast. Clear? Okay, so let's move on. Let me tell you one more point. Now the point is, if branching is same, then plus I power is directly proportional to the number of carbon atoms. What does that mean? Have a look, guys. I'm going to take one example. Just a second. See, what it's saying, if branching is same, over here branching was different. Over here branching was different. Now if branching is same, then plus I power is directly proportional to the number of carbon atoms. What that means exactly? What that means exactly? See guys, for example, this is CH, right? This is CH3 over here, right? This is, for example, CH2, this is CH3, right? And this is, for example, the free valent carbon which is attached with the carbon chain, right? So this is the free valent carbon which I'm talking about, correct? Now, see guys, this is CH, for example, this is CH3 in this case, this is one more CH3, right? And this carbon over here, I'm calling it as the free valent carbon because it is attached with the carbon chain over here, right? So if I ask you, is the branching same present at the free valent carbon, right? This is the branch, this is the branch, so two branches at the free valent carbon, right? This is the branch, this is the branch, so two branches again at the free valent carbon, right? And I told you a few minutes back, if branching is same, so branching is same in both the cases, then plus I power is directly proportional to the number of carbon atoms, right? See, in this branch there are two carbon atoms, right? In this branch there are two carbon atoms. In this branch there is one carbon atom. One carbon atom in this branch, one carbon atom in this branch. So wherever you'll be having more carbon atoms in the branch, there only plus I power of the group will be more, right? So plus I power of this group will be definitely more than that of plus I power of this group, right? So do remember this thing as well. So whenever branching will be same, then you are going to decide on the basis of number of carbon atoms present in the branch. Wherever number of carbon atoms in the branch will be more, that group only will be having more plus I power as compared to the group which has got less number of carbon atoms in the branch, right? As simple as that. Perfect. So let's talk about a few more interesting things. People, you would have discussed about the isotopes of hydrogen, right? Protium, deuterium and tritium. Protium, deuterium and tritium, right? Okay, see, this is basically H, atomic number 1, mass number 1. This is H12, this is H13, right? This isotope of hydrogen is what I call as protium, this is deuterium, this is tritium, right? Which I'm simply representing by protium H, deuterium D, tritium T. Remember, all these basically show the plus I power. All these basically show the plus I power, right? And do remember the plus I power of tritium is always going to be greater than that of deuterium, but it's always going to be greater than that of normal protium. Yes? Right, people? Clear? Now we are going to talk about some questions which are going to make all these concepts clear to you, right? Yes? See guys, arrange the following according to the minus I power, right? Can we arrange them? Can we arrange them on the basis of their minus I power? Can you let me know fast? Yes? Okay, people are saying yes, we can do that, yeah? So let's have a look. we are going to arrange them on the basis of their minus I power, right? Let's say this fluorine is attached with a carbon chain. I'm assuming this chlorine again attached with a carbon chain. This bromine is attached with a carbon chain, and this iodine is attached with a carbon chain, right? Have a look properly. Okay. Now, among fluorine, chlorine, bromine, and iodine, which one is more electronegative? Fluorine. If fluorine is more electronegative, this fluorine is going to drag, it's going to pull the sigma electrons towards itself, right? Since fluorine being maximum electronegative, it's going to bring out maximum sigma electron density from the carbon chain, right? So I'll say fluorine is going to show maximum minus I, followed by chlorine, followed by bromine, followed by iodine, right? As simple as that. Yes. Now similarly, let's assume this fluorine is attached with the carbon chain. Over here OH group attached, over here NH2 group attached with the carbon chain. So basically fluorine is directly attached with the carbon chain, and over here oxygen is directly attached with the carbon chain. Nitrogen is directly attached with the carbon chain. We know the electronegativity of fluorine is greater than that of oxygen, greater than that of nitrogen. So this fluorine will be having more tendency to drag, to pull the sigma electron density towards itself. So this fluorine has got more plus I, followed by this OH, followed by this NH2, right? What about this NH3 positive and NO2 positive, right? I told you a few minutes back only, all the cationic groups, their minus I power is always greater than that of the neutral groups, right? This is the cationic group, this is the neutral group, right? So plus I power of the cationic group is more than that of plus I power of the neutral group. Yes? Right, people? Similarly, if you talk about OH and NH2, over here oxygen is attached with the carbon chain, right here nitrogen is attached with the carbon chain. Oxygen being more electronegative, it's going to pull the sigma electron density more towards itself, right? So this OH will show more minus I as compared to this NH2, okay? Right, people? Clear? Is it clear to everyone? Yeah? Now similarly, is it plus I or minus I? We are talking about minus I, right? We are talking about minus I. Yeah? Cationic group shows more minus I than that of the neutral group. Correct? This is the cationic group. That's why it's showing more minus I than that of this neutral group. Okay? Yes? Now, let's talk about a few more cases. We have got C triple bond N attached with the carbon chain. We have got CH double bond NH attached with the carbon chain. CH2 single bond NH2 attached with the carbon chain, right? See guys, this carbon, it is forming 2 sigma bonds, so it's sp hybridized. This carbon is forming 3 sigma bonds, sp2 hybridized. This forming 3 sigma bonds, sp3 hybridized, right? So, electronegativity of this carbon is more than that of this one, because of the more percentage S character, right? If electronegativity of this carbon is more, that means in general this group has got more tendency to drag the sigma electron density towards itself as compared to this group, So minus I power of this group is more than that of this, right? So 1, 2, 3 is going to be the order. Right, people? Clear to everyone? Let me do in the charts fast, if every single thing seems clear to you. Okay? Perfect. So let's take few more cases. Can you let me know fast? What is going to be the order over here? Can you let me know fast? What is going to be the order in the 6th case? I'm waiting for your answers. Chit, because whenever we talk about plus I and minus I, we take reference as hydrogen, right? In the first case itself, if you remember, I replaced hydrogen by some group. So hydrogen, this plus I and minus I, it is measured with respect to hydrogen. So hydrogen is taken as a reference. So people are saying 1, 2, 3 is going to be the order. Is 1, 2, 3 going to be the order? Let's have a look. See, we have got C double bond O. Oxygen being more electronegative, delta negative on this oxygen, delta positive on this carbon. Similarly, delta negative over here, delta positive on here, right? Over here, nothing. Now people, this carbon carrying positive charge, again this carbon carrying positive charge, this carbon does not have any charge. If I ask you now, so first of all, before talking about the charges, this carbon is sp2 hybridized, right? Because it's forming 3 sigma bonds. This carbon is again sp2 and this carbon is again sp2, right? Okay, all these carbon atoms are sp2 hybridized, right? This is having positive, apart from sp2, this is having positive, this does not have any charge. Where is the intensity of positive charge more? Can I say intensity of positive charge is more here, right? Because this carbon is attached with more electronegative element, right? Wherever intensity of positive charge on carbon will be more, then only this group, I'll say this group will be having more tendency to drag the sigma electron density towards itself, due to which this is going to be the minus I power, right? This is going to be the order of minus I power, as simple as that. Yeah? Yes? Now, if you talk about NF3 and NH3, NF3 and NH3, definitely this one, because nitrogen is attached with fluorine, right? Fluorine is going to attract the bonded pair towards itself, due to which the intensity of positive charge over here will be more than that of intensity of positive charge on this nitrogen, right? If the intensity of positive charge is more in this nitrogen, that means this nitrogen is going to drag more sigma electron density towards itself. That is why this NF3 positive group, it shows more minus I power than that of NH3 positive group, right? Okay? Right, people? See, positive charge on nitrogen, positive charge on phosphorus, positive charge on arsenic, positive charge on antimony, right? Nitrogen, phosphorus, arsenic, antimony, they belong to the same group, right? They belong to the same group. Okay, and in the group, volume charge density dominates over electronegativity, if you remember. Wherever size is less, positive volume charge density will be more, right? Because volume charge density is directly proportional to charge, inversely proportional to size. Wherever size will be less, there only positive charge density will be more. Can I say positive charge density on this group is more than that of this group, more than that of this group, more than that of this group? Wherever positive charge density is more, that group is only going to drag the sigma electrons more towards itself, due to which this group shows more minus I, followed by this, followed by this, followed by this, right? This is going to be the order. Okay, wherever positive charge density is going to be more, there only minus I power of the group is going to be more, right? See, oxygen, sulfur, SET, they are again the same group elements. Again, VCD comes into play, volume charge density. This group has got lesser size. Lesser size means more positive charge density. So positive charge density of this group is more than that of this group, more than that of this one, more than that of this one. Wherever positive charge density is more, that group only will be having more tendency to drag the sigma electrons towards itself. So this group is going to show more minus I, followed by this one, followed by this one, followed by this one, right? What about in this case, guys? NR3 positive, NH3 positive. It's again a very simple case, but this is the slight exception over here, right? We have got nitrogen. This is attached with a carbon chain. There is a positive charge on nitrogen. This is R, this is R, this is R, correct? Then we have got NH3 positive as well. This is N, this is H, this is H, this is H. Nitrogen carrying the positive charge, right? In the last session, if you remember, what does R mean? R means alkyl group. R means alkyl group, any alkyl group, okay? R means alkyl group, yes? Okay. Now people, in the last session, if you remember, I told you bond angle is directly proportional to percentage S character, which is directly proportional to electronegativity. Do you remember this statement which we discussed in the last session? Bond angle is directly proportional to electronegativity. That's something which we discussed in the last session, right? Do you remember that? Do you remember, people, in the last session we talked about that? Now, normally, what a normal person will think, he will think like this. For example, these are the methyl groups. For example, these are the methyl groups. Methyl groups, they will push electron density towards the nitrogen, due to which the intensity of positive charge on this nitrogen should be less than that of the intensity of positive charge on this nitrogen, right? Which should make this group as less minus I showing as compared to this group. So normally this group should have less minus I power as compared to this group, right? As compared to this group. But the case is reverse. See, over here you have got alkyl groups attached, right? Alkyl groups are basically the bulky groups, and if they are the bulky groups, they'll exert repulsions. And if they'll exert repulsions, can I say bond angle would have got increased in this case? If bond angle will be more in this case, more the bond angle, more is the electronegativity. So electronegativity over here is going to be more than that of electronegativity over here, right? Wherever electronegativity is more, there only tendency to drag the sigma electron density towards itself will be more. And wherever tendency to drag the sigma electron density will be more, right? That group only shows more minus I power. So among these two, it looks like this group should have more minus I than this group, but the case is reverse. This group has got more minus I power than that of this group. I'm sure it's again clear to you, right? 1 is greater than 2. Yes? Perfect. Okay. This is the minus I series which you need to remember, my dear people. Okay, this is the minus I series which you need to remember first of all. NF3 positive showing maximum minus I power, followed by NR3 positive, followed by NH3 positive. Then we have got NO2, then we have got CN, we have got COH, we have got COOH, we have got fluorine, chlorine, bromine, iodine, right? We have got OH, we have got OR, we have got C triple bond C, phenyl ring, strained ring. What is strained ring? Strained ring is that cyclopropane or cyclobutane, right? Wherever you have got the angle strain, okay, this is the strained ring. Then we have got hydrogen over here, right? Normal protium. This is basically the series which all of you must remember, and do take the screenshot of this series, right? This series is going to help you a lot in solving the equations based on the acidic strength and basic strength, right? So do take a screenshot of this series. Okay, this NF3 positive is going to have maximum minus I power followed by NR3 positive. Similarly, there's a series for plus I as well, and this is the plus I series. This is the plus I series, right? CH2 negative, it's going to show maximum plus I power followed by NH negative, followed by O negative, C double bond O negative. Then we have got 3 degree alkyl, we have got 2 degree alkyl, 1 degree alkyl, SiH3, CT3. This T is tritium, this D is deuterium over here, right? This is normal CH3, H is protium over here, right? Then that of tritium, then there is deuterium, then there is hydrogen as well, protium as well, okay? This is one more series which you need to take a note of, correct? I'm going to use this series in the questions to decide the acidic and the basic strength, right? So do remember this series from now onwards, correct people? Okay? And do remember one more thing, both plus I and minus I effect, right? Both plus I and minus I effect, these are considered only up to 3 carbon atoms. After 3 carbon atoms, their effect is neglected, okay? Their effect is neglected. For example, this is carbon, 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 right? It's a carbon chain. It's a carbon chain, for example, right? Let's say I've got C triple bond N, we have got CN group attached with this carbon chain. This is going to definitely show minus I power, right? So it will pull the sigma electron density towards itself. So the first carbon with which this group is attached, it's going to have maximum delta positive charge. As you go far from the group, the delta positive will keep on decreasing. This was maximum, this is lesser than it, then delta positive is lesser than it, right? Again delta positive, it will keep on decreasing, right? And this inductive effect, it's only taken till 3 carbon atoms, right? After 3 carbon atoms, its effect is neglected. Its effect is neglected after 3 carbon atoms, okay? Similarly, if I'll be having, for example, we have got this is the carbon chain, this is the carbon chain, for example, and there is a group attached which shows plus I power, which shows plus I effect, right? There is a group attached which shows plus I effect. So this group is going to induce the sigma electron density in the chain. So maximum electron density will be towards this carbon, right? If you move far from it, the negative charge on this carbon will be slightly less, negative charge on this carbon will be slightly less, and as you go far, its effect is neglected, right? Okay, so do remember this as well. Okay, now people, it's time to solve certain questions based on the inductive effect, right? Time to solve certain questions on the basis of inductive effect. Have a look, guys, have a look properly. Arrange the following according to the stability order. Basically, these are the carbocations, which is something we are going to discuss afterwards, right? Not here. Okay, the stability of carbocations is discussed in many ways by means of hyperconjugation, right? Plus H effect plus hyperconjugation, that increases the stability of the carbocation. Even resonance increases the stability of the carbocation. Plus inductive effect is also going to increase the stability of the carbocation. But right here, I'm not going to talk about hyperconjugation, resonance, mesomeric or whatever. I'm not going to talk about any other effect. I'm right now talking about inductive effect, and I want you guys to arrange them on the basis of their stability order on the basis of inductive effect, not on the basis of any other effect, right? Have a look how these sort of questions are to be solved, okay? See, one thing I would like to tell you. Do remember one thing. More the charge on the molecule, more is going to be the potential energy of the molecule, and less is going to be the stability of the molecule. Do remember this thing as well. More the charge on the molecule, more is going to be the potential energy of the molecule, and less is going to be the stability of the molecule. So whenever you need to compare the stability of the charged species, basically, okay, you need to say exactly where will be the charge minimum. Wherever charge will be minimum, there only stability will be maximum. Now have a look properly what I'm going to talk about. This is important and basic at the same time. Yeah, have a look, guys. This carbon is attached with 3 hydrogen atoms, and this carbon having positive charge. This carbon is having positive charge, this carbon having positive charge, and this carbon having positive charge, right? With this carbon, there are 3 hydrogens attached. With this carbon, there is a CH3 group attached, alkyl group, methyl group. There are 2 methyl groups attached. There are 3 methyl groups attached over here. Methyl groups, they show plus I effect, right? So this methyl group is going to show plus I effect over here. So it's going to increase the sigma electron density towards this carbon. It's going to send some sigma electrons towards itself, right? Over here, 2 plus I showing groups. And over here, 3 plus I showing groups. right? What these alkyl groups are basically doing, these alkyl groups are basically sending the sigma electron density towards this carbon carrying positive charge, this carbon carrying positive charge, and this carbon carrying positive charge, right? Wherever alkyl groups attached are more, there only can I say the magnitude of positive charge over here will be minimum among all. Can I say the magnitude of positive charge will be minimum among every carbon having the positive charge? Why is that? Because this carbon has got 3 alkyl groups attached with it, right? All the 3 are going to show plus I effect, right? Plus I effect showing groups, they are going to push the sigma electron density towards this carbon, right? Due to which what happens? I'll say the positive charge density on this carbon will be minimum over here, right? The magnitude, the intensity of positive charge on this carbon will be minimum, right? Wherever the charge is minimum, there only stability is maximum, right? So this is the stability order, I must say, right? Okay, as simple as that. Similarly, there's a carbon having negative charge, this carbon having negative charge, this carbon having negative charge, right? So this is plus I showing group. You have got 2 plus I showing groups over here, and you have got 3 plus I groups showing over here, right? What these plus I groups are going to do? They are going to increase the electron density at the center, right? They are going to increase the electron density at the center. So I'll say already this carbon was having negative charge. Now due to these plus I groups, there will be more negative charge at this carbon, right? More the charge, less the stability, right? So stability of this one is going to be minimum among all, right? As simple as that. Correct, people? I'm sure it's again clear to you, right? Okay, let's not do all the questions in the tonight session, because I've got one more session coming up at 10:30 sharp on Vedantu JE English. You guys can join in that too. That is going to be the KVPY mock test, right? Let's do all these questions. These questions let's try to do in the next session, right? The next session I'm going to start with these questions, and after these questions we'll move on to one more effect. That is something which we call as the resonance effect, right? Yes. Somanatha, there is no need to learn nomenclature. I'm after a few days only I'll be taking one shot in which I'll be doing the complete nomenclature, right? Just in I guess 1 or 2 hours. That's all. In 1 or 2 hours I'll be finishing the whole nomenclature. Yes? Okay. Anyways, you can take this question as the homework. This question you can take as the homework. You can let me know its answer in the comment section, and the ones who have not liked the video, please do like the video. Why are methyl groups showing plus I effect? Shriniti, I think you have joined late. I have given answer of this question long back. You can go back, drag the video a little back, you'll get your answer. Okay, so people, let's stop with this. Rest we'll be doing in the next session, right? The next session, I'm going to start with the question which is on the screen. Do let me know its answer in the chats, yeah, in the comment section. And the ones who have not liked the video, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. With this, I'm going to take a leave. I'll see you guys at 10:30 on Vedantu JE English channel, yeah? Bye-bye guys, take care.